So I haven't really put a lot of thought into what video I'm making today. Just that I haven't really put a video out in quite a while, and I do like the sound of my voice. And really, I just want. I don't know what I'm going to do. Um, this may turn out to be the greatest tech video blog ever created. By the end of this, we may solve some of the world's toughest problems. Or, or not. I don't know. Uh, I have a lot of servers, and with these servers, I host websites for for people, that give me money in exchange for uh, servicing their website, making it look pretty, stuff like that. What what a lot of my clients don't know is that their servers, their website is practically living 8 feet away where I eat breakfast every morning. A wall separates their website and or their entire production uh, production workloads and my television where I'm watching a movie. When I first started, I did have an office for a while, and electricity and rent sucks. I don't like bills. I just don't. So I put a lot of thought into getting the exact quality and same level of same level of redundancy that any client would get if uh, my infrastructure was not in a guest bedroom. And I pretty much have achieved it. Any unless the half of the United States loses power again, like we did years ago, I should be all right. And even then, I do have a backup propane generator. I'm not running crazy workloads. I mean, a lot of it is for developers who are just using it to test. There are some critical websites and stuff like that. So I ended up investing a lot of money into equipment. You go to if you have a your internet in your house, your router, a Wi-Fi router, maybe the cable company gave it to you, or maybe you went out and bought that new fast Wi-Fi router, and it's a couple $100. I bought a switch off of eBay when I first started out, and it was $3,000. And I plug it in, and I'm all happy because it's very fast, 10 gigabits per second. And that's really how I learned a lot about command line interface and how to set that up. No, that's not my point here. So I have these racks of servers, and in each rack there is a switch, and each of those switches, they're very fast, um, and they cost quite a bit of money, and they have all these nice features, and every single one of the ports on that switch runs at an incredible speed. So I have I think a 52 port switch, and 48 of those ports run at 10 gigabits per second. Um, and four of those, the other four, uh, they're uplinks, and they run at 40 gigabits per second, which is absolutely fantastic. And for redundancy, usually you should have two of those switches in each rack. I don't have that. I have one, but for my configuration, it's more than enough. Now, depending on how much experience you have with a switch, some issues do arise. Have you ever been to a concert and or played in a band, and a microphone got too close to a speaker and you just heard a shrieking feedback loop? Well, switches have something very similar to this. I'm going to draw. I'm going to whip out my trusty paint program here. So, let's draw our beautiful shiny switch. And it's got ports. You get the idea. And it keeps going. That should be an arrow. And each of these ports, 10 gigs, 10 gigs, 10 gigs, 10 gigs. And then off around here, you got four ports that are 40 gigs. Now these ports link up to the router that goes out to the cloud. So this is our puffy cloud here, and this is the internet. I don't like this picture. Let's get rid of this. So the reason behind that is because you have all your computer equipment, servers, and devices, and they all get a nice high-speed 10 gig link to the switch. Okay. But now, if that traffic has to eventually leave the switch is more of like a transit. It's a way to get somewhere else. You want to get out to the internet. So it unless if this server here wants to talk to this server here, the traffic would do this. It would go here and then come back out here, and then this guy will probably want to respond and say, hey Bob, I got your request, and here's that file you asked for, and it goes back, and the router does not get involved, and you have a nice high-speed link. Fantastic. So now, most most likely though, uh, these devices not only want to talk to each other, but they also want to talk to other devices that are outside of your data center. They want to reach out into the internet, you know, and then this router will talk to another router and another router, and then make its way to, you know, let's say this is a huge, vast distance, okay? And on this side of the line is in another state, let's say. And somebody's on their computer and they go to www dot some website.com, and that website is this guy right here. All right, so his traffic finally makes its way to my router. My router says, "Yep, I know where that web server is," and sends the request down to the switch and to that server, and the server's going to respond and do the same thing backwards. Now, if you have a few hundred of these servers, and they're all running, they're all talking to the switch at 10 gigabits per second, um, and they all try to speed. They all want to get out to the internet at the same time. They're definitely not all going to be able to uh, go at the speed of 10 gigabits per second if all you have in the switch are 10 gigabit ports. So that's why usually most high quality switches will have uplink ports. So my specific ones have 40 gigabit per second ports. So I have an aggregate of 40, 80, 120, 160. So 160 uh, gigabits per second going to out to the router and out to the internet, so that I don't have a bottleneck here. So that shiny, expensive switch uh, does its job properly and it works. Now, I'm going to go into a little bit of a networking lesson. So, uh, in, in a data center, like the very small one that I have, you have racks. And each one of these racks hold a boatload of servers. And you have, let's say, you have 30 racks. I'm not going to draw 30 racks, but I'm going to make believe that there's 30 here. We'll only see 3. And on top of each of these racks, there's a switch. There's a one of those switches that we were just talking about. Nice, expensive, shiny switch. Okay, and there's a certain way that these switches should be wired together. Uh, they're called best standards and practices, and very smart people come up with these standards of how uh, any reputable company that wants to be looked at as a serious, responsible hosting company or whatever service you're providing, this is the way it should be wired. Um, a lot neater than this, so I think we're going to switch programs here. Let's actually hop onto the web. So, when properly wired, you have these very expensive switches. You have one on each inside of each rack. And then those switches eventually connect to other switches. So all the switches connect to each other. And then all those connected switches connect to an even bigger switch, a core switch. I'm gonna show you this. I'm just waiting for my very slow computer to boot up. And when all of that is wired together, it's called a network fabric. And I'm going to show you what that looks like. Let's good old Google image it. I'm getting at something here. There is a point to the story. So let's find one that's relatively simple and not doesn't have a lot of extra stuff that we're not discussing. Yeah, let's take this one. All right. Yeah, I don't like that one. Um, hmm. Here we go. We use this. All right. I'm gonna steal this image. Oh, and it's called the leaf spine topology, by the way. That is the most popular one. Okay, so let's see. There's probably stuff that. Let's go back to paint. Okay. Where did I? Let's do it like this. There we go. All right. So here is my data center. Okay. Here you have racks. These are the racks of servers. Okay. And at the top of each rack are these switches. Um, at at $3,000 a pop, they get it gets really expensive really fast. And each of those switches then connect to an even more expensive switch, which is called a core switch. And these are the ones that are up here. Now I do not have. I only have two core switches, and that is more than enough for uh, my what I needed for. Now you see how each of these. So this switch, let's call this switch here switch number one. Oh, brushes. All right. This is switch number one, two. You get the point. And these are all the connections. So this switch here connects to every other switch. It has a cable going to every other switch, And that's so that if, let's say, this link here were to go down, it would then switch over to this link. So there's redundancy built in. So now I'm getting to the point, and what the whole purpose of the reason I'm bringing this up. So if this switch here, right, costs $3,000, and it has uh, 30 ports, okay, on it, and each port, uh, the bandwidth or the speed that that operates is 10 gigabits, 10 gig Ethernet, right? I completely messed that up. 10 gigabits per second, okay? And you have 30 of those, okay? So you're you're paying each for each port. If you pay $3,000 for the switch, it's costing you $300, right? Is that right? Wait, so 30. Let's see. All right. So if the switch is $3,000 and it has 30 ports, it's $100 that you're paying per port, per connection. All right. Now, switches work at layer 2, and now I'm going to go back to my uh, microphone loop. Switches have, you cannot connect, if you have this wire going here, okay, um, and you were to take another wire and plug it here. So now this is 10 gigs. Oops. This link is 10 gigs. This link is 10 gigs, right? So now you're getting a 20 gig link up to the switch, right? If you think that, you are in serious trouble, because what will happen as soon as you plug this second wire in, a loop starts to form. And with a 10 gig link, it happens pretty fast, a few seconds. You'll notice that the lights on the switch will start to blink rather quickly, and the data on your internet, your entire network will come to a screeching halt. Um, and the reason being is there's a loop happening there. In layer 2, if you connect two switches with more than one cable, okay, so here's one, it goes here, and here's another, and it goes there. You may think that, well, wow, I can get a much faster link. I can connect 6 cables and have a 60 gig link between these two switches. And at $100 a port, you would definitely want that, right? Because you want to make you want to make the most use out of every port that you have. Okay, so if you connect each server up to your switch, and you have 10 leftover ports, what you should be able to take those 10 ports and wire them up to your next switch, so you're using all of the bandwidth that you paid for. But it doesn't work, and the smart internet standards people didn't find a way around this, but came up with a fail-safe so that if the new guy starts work and doesn't know this, and has this brilliant idea and starts connecting cables, what will happen is there's something called spanning tree. I'm not going to actually spell this out with a mouse, but it's called spanning tree protocol, and it is able to see, hey, uh, I see two paths, right, to the same location. So I don't want a loop to form, so I'm going to block all of those ports. I'm going to shut down every port except for one port. And that's how you're able to get away with the way this is connected. This went a little too far there. So this diagram is misleading because even though you have a link to, you have multiple links to each switch, spanning tree is there, and all of these links are blocked. The port is literally shut down except for one. So there's really only one connection from here to this switch, from here to this switch, and between each switch. Why would you want to have? Why would you even put a wire there if the port is shut down? Well, wires do fail, and spanning tree not only monitors if there are two cables or two paths to a switch, but it also will be able to tell that this link went down, and once it realizes that a link went down, it will unblock one of the other connections and reestablish a connection. Okay? But that's in a situation where there's a failure. But 99.999% of the time, you have all of this bandwidth that's not being used. It's like buying a car with a 500 horsepower engine, but the pedal won't go past 20 miles an hour. So even though the engine is more than capable to get from point A to point B in 2 seconds, you're going 10 miles an hour, and it's going to take you an hour and a half to get to grandma's house. So there have been every now and then these new methods have come up to get more than one connection between these switches, and they're very buggy, and none of them really worked very well. But now, recently, with network virtualization, people started to realize that we don't need a layer 2 connection anymore between these switches. Yeah, switches you would usually just work at layer 2, but if you're spending $3,000 for a switch, trust me, it's not just doing layer 2. It is very capable of running IP protocol between the switches. So a better way is now this $3,000 switch can, instead of you doing MAC addresses and having that layer 2 link, you can put an address, an IP address on each port, and have and route, literally use IP routing between every switch, and it scales. A layer 2 broadcast domain really cannot get that big because uh, the more computers and servers that are on that one layer two domain, the more traffic there is. There's more broadcast traffic. Our all of every device on the internet chatters, and every other device on the internet will see that chatter, and it'll clog up uh, your network after a while. Layer two definitely has a limit to how many um, computers can be on one layer two broadcast domain. So now we have something called EVPN. Okay, um, you can use any routing protocol you want. BGP is a big one. That's the one that I'm going to use. BGP or OSPF are the two most popular. I would say BGP or IBGP is probably used more than OSPF. Um, but both work equally as well. And one last ingredient is a little network virtualization in there, which is VXLAN. All right, so we have three ingredients: EVPN, BGP, and we have VXLAN. All separate and all have their uses, but something amazing happens when you put these together. So I really need to get a drawing board so that I can move away from this mouse so I can actually draw something. All right. So no more layer 2 links, okay, between these switches. Uh, each port, each switch is going to have a loopback. That was an O. Okay, and it'll have a loopback address. And it'll have a port address. So this this switch could be 2.2.2.2. This one would be 3.3.3.3, 4.4.4.4, 5, 6. You get the point. This switch would be 777, 8, and so on and so forth. And there's several ways of doing this, but each switch can have its own AS number, its own AS number, autonomous system. Um, so this switch would be 6500. This switch 6501, 6502, 6502, 3, so on and so forth. And BGP takes care of routing all the traffic freely between this. So now what you have once this is all wired up is you have a routing table, and you have multiple paths. So now your servers that are down here uh, needs traffic uh, to go out to the internet. It can get to the switch, and this switch can easily load balance traffic between every single NIC. And there's load balancing in there, congestion uh, management, using BGP, and now you are getting out of that switch every dollar you paid for it, because you're using every single port on that switch, and they are all running at the speed of the port, and there are no links that are blocked. This does cause a problem. Okay, so now if it was just BGP, we'd have an issue, because most I'm gonna go out on a limb here and say that 90% of the time in these servers you're going to have VMware or a hypervisor of some sort, usually a VMware ESXi hypervisor. All right, and one of one of the biggest features of virtualization and VMware is being able to move or live migrate or vMotion or storage vMotion uh, virtual servers from one server to another. Now, this was very easy and simple when this was layer 2, and no matter where you plugged that server in, it was on the same layer 2 network. Let's say the network was 10.0.0.0/24. So let's say it was on this network here. All right. So the 24 is saying that you have 254 addresses in the subnet. I mean, in this network, and no matter where you plug that computer in, wherever that computer went, it would be fine, because if it had a IP address of 10.0.0.1 and it moved from here to here, everything would just be A-OK. It could keep this address, and this rack here is in that same subnet, 10.0.0.1. And all that really would happen would be an ARP, the hypervisor will, once the virtual server moves, wherever it moves to, that hypervisor will send out a gratuitous ARP message to the switches. And basically what that is, a gratuitous ARP is the hypervisor saying to the switch, hey, you may want to put this into your database, or into your TCAM, that this MAC address is now on this port, and it would update the table in that switch. But now, with every single port having its own subnet, this complicates things quite a bit. But fortunately, several years back, network virtualization came out. Now, at first, this did not have hardware support, and there would be no way that you would be able to use VXLAN between switches, because there would just be too much overhead. Uh, every switch it would need too much processing power if it was an older switch and just did not have hardware VXLAN built into it. But now switches, you can buy a switch that has hardware supported offloading for VXLAN for almost all of the virtual tunneling protocols. So it's going at line speed. So you're routing at line speed, and VXLAN, I'm going to get into the nuts and bolts of exactly what is going to happen. Uh, but it, what has happened is that technology has caught up, and the switch is able to route at line rate, which that's that's been possible for uh, many years. But the new thing is VXLAN. Now these same switches can tunnel at line rate as well. Um, so what this creates is two networks. You have your routed network, which uh, is that initial set of subnets and IP addresses that each switch and each plug will have, and we call that the underlay network. And you don't need anything fancy there. You just need IP connectivity between switches and down to the hypervisor. The hypervisor too. It's not layer 3. It's not layer 2 anymore. The hypervisor will have a IP address on its virtual switch, and it will also be running BGP, and it will peer. So the hypervisor in this rack will peer with this switch, and then this switch will peer with that switch, and this switch, and so on and so forth. I'm going to pause it right there because this is very long winded, and I want to get into the actual configuration of this. So, this is a good place to stop for right now.